Cool, thanks. All right, so I'm going to talk about how we can get Byzantine agreement from what I call the internet hypothesis. So, the kind of the inspiration for this work is, the observation that we ended up with this thing that we call the internet, right? Why is it that we ended up with the internet? We could have had a bunch of different networks, all of which spoke, IPv4 and IPv6. And of course, the technical answer is, well, the structure of the current internet has arisen in a decentralized way from these individual peering and transit relationships between different networks. And kind of what's happened is that it turns out that transitively, everybody wants to talk to everybody, right? In other words, we all want to talk to someone who probably wants to talk to Google, and so everybody else wants to talk to somebody who talks to Google or one of these other big players. And so in the end, it just made sense to have this one globally connected network. And if you were an ISP and you tried to sell access to some other network, nobody would be interested, right? If they can't get access to all the existing sites that they're used to talking to. So the question here is, can we have systems that similarly manage to agree on kind of the global consensus state, leveraging these same kinds of dynamics? And the hypothesis is that, in fact, there are other relationships that are a lot like internet peering. And in fact, you can already kind of see this in global payments and payment networks, where you have kind of small banks that use correspondent banks that you go through these clearinghouses, and in effect, a clearinghouse like Standard Chartered is kind of like the tier one ISP of international payments. But kind of coming back to what I was saying, it's kind of we're not in a kind of one person, one vote regime here, right? We're saying that, okay, if some random webcam drops off the network, nobody cares, right? If Google drops off the network, people think there's a serious problem. So there's this kind of market-based notion that there are particular people we really want to agree with, and the cost of kind of going off and not agreeing with those people is so high that nobody is going to be able to bear it. And so if we hypothesize that we have this kind of dynamic, can we build a Byzantine agreement protocol? So more concretely, what this means is that you basically say, look, here we are in San Francisco, I have this friend in Mumbai, I really want to agree with, and so we're going to get together and we're going to just make sure we never disagree on anything. But we also have other friends, and we're not going to agree on anything until our other friends have agreed, and they're not going to agree until their friends have agreed, and so on. And so by the time anyone agrees to everything, essentially the whole world has agreed that it's already happened. And so what's cool is that this includes not just the people you directly want to ensure you agree with, but probably anybody that in the future you'll decide you wanted to have agreed with, right? If this kind of transitive internet-like property holds, right? And so this is the approach that is in use by the Stellar blockchain, which is like a multi-asset blockchain with kind of a built-in DEX. And one of the advantages of this in Stellar is that it lets you, if you want to go from asset A to asset B, you can do a transaction that involves trading through asset B. So you trade A for B for C. You do that atomically, and you can do that even if you don't trust the asset issuer from B, because the whole world agrees that both hops of your transaction happened atomically. Okay, but I'm mostly going to talk about consensus today, not about blockchains. What this means for consensus is that we need a kind of new variant of the traditional Byzantine agreement model that can accommodate this kind of basing security on the internet hypothesis instead of just this kind of node counting, which is what usually happens. You assume 2/3 plus 1 of nodes are honest. So what I've developed is this thing called Federated Byzantine Agreement, which is a model that's based on Byzantine Agreement, but of course Byzantine Agreement is vulnerable to these Sybil attacks, where some bad guy creates 1 million nodes, and then that bad guy controls an overwhelming majority of nodes, right? So the idea is we're going to defeat Sybil attacks by choosing our quorums in a decentralized way based on this thing called a quorum slice. So what is a quorum slice? A quorum slice is basically is a decision by a single participant in the network to choose a set of nodes that it thinks is sufficient to speak for the whole network, right? So I might say, my quorum slice is, Google, Amazon, Facebook, Stanford, right? And I'm not going to agree to anything unless they do. Now, for kind of fault tolerance, I might want to be able to handle individual machines crashing. So maybe like, Stanford runs 3 machines, and I want to make sure that at least 2 of them agree with me, and so same for like Facebook and Amazon. So you can do that too by having multiple quorum slices, and that encodes some amount of redundancy. So in the case of Stellar, where we use this for a decentralized exchange, the people you want to make sure are in all your quorum slices are the people who issue the tokens that you care about, right? So if at the end of the day I'm trading digital dollars that I can redeem at Wells Fargo, when I get paid, I want to make sure Wells Fargo agrees I got paid, because like if they agree I got paid, then ultimately I can redeem those tokens, even if all hell breaks loose and the network partitions and all kinds of weird stuff happens. Okay, so given this model, we can define a federated Byzantine agreement system as a set of nodes V and a quorum function Q, where Q of a node little v is basically the set of quorum slices chosen by that node V. And then we can say a quorum is a set of nodes that includes at least one slice of each of its members, right? And this is just kind of the key definition that kind of differentiates federated Byzantine agreement from traditional Byzantine agreement. And so we can kind of explore this with a very simple example where here each node has only a single quorum slice, and I've depicted that by drawing arrows from the node to the other members of the quorum slice. You can see that V2, V3, V4 is a quorum because it is the quorum slice of each of its members. And similarly, and V1, V2, V3 is a quorum slice for V1, but it is not a quorum because it doesn't include a quorum slice of V2 or V3, right? The smallest quorum, including V1, is going to be the set of all nodes, right? So in case you haven't seen it, I have to do like kind of one more realistic example to show how this works in practice. Let's say that we're using this for payments, and like I was saying before, there's kind of some tier 1 notion of banks, and then like smaller banks and credit unions and individual users. And so maybe the top tier turns out to be like the top 4 retail banks in the US. But because this quorum slice selection is decentralized, not everybody has to agree. So V7 and V8 might say like, okay, we realize we have to like be in sync with like the main banks in the US, but we think they're evil. We think they're gonna, rip us off the minute they get the chance. So that's fine. V7 and V8 can extend their quorum slice and say, you know what, we're going to depend on, 2 out of these 4 big banks before we think anything happened. We're also going to require one of these 3 nonprofits to agree because they have very differently aligned incentives. And these nonprofits might depend on kind of 2/3 of each other plus 3/4 of the main ones here. So just to kind of see how this plays out, if the kind of suspicion was correct and the big banks are evil, suppose Citibank is evil, Citibank goes to V7, says, hey Citibank, here's $1 billion, we're using blockchain, irreversible, whatever, so let me quickly walk away with $1 billion worth of goods, I'll fly away with my fleet of airplanes you just sold me, and you'll be happy that this transaction is irreversible. V7 says, not so fast, I need agreement from a quorum, right? And my quorum requires 2 out of 4 big banks. Okay, check, got that. I also need one of these nonprofits. That nonprofit needs another nonprofit. Okay, we're good. Have a nice day. Fly off with your fleet of airplanes. Then Citibank colludes with the other two of the other big banks to roll back that transaction, take back the $1 billion, goes to V8, says, hey V8, I'd like to buy your fleet of airplanes, blah, 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 like let's just do this. V8 says, okay, well, I need 2 out of the 4 big banks. The banks are evil, so they're going to pretend that $1 billion doesn't belong to V7. But V8 also needs a nonprofit, right? And so maybe he gets unlucky and he talks to the ACLU, who is lagging behind a little bit and didn't see that $1 billion was paid to V7. But the thing is, the ACLU depends on at least one other nonprofit. So the ACLU is saying, well, I'm not going to sign off on this, I'm not going to agree because Stellar and EFF aren't agreeing. And so V8 will not fall for this attack and will hold on to its fleet of airplanes, which is kind of exactly what we wanted. Okay, so now I want to talk about how you turn this model into a Byzantine agreement protocol. And so first, I want to give a little bit of background on Byzantine agreement, and at least the way I think it makes sense to look at Byzantine agreement algorithms, because they're all described in different ways, and so it's kind of nice to have a framework where you can sort of compare them a little more apples to apples and see what's different between all these protocols. So And when I say Byzantine Agreement, I don't include Bitcoin as a Byzantine Agreement protocol. I can consider Byzantine Agreement a specific kind of consensus protocol, one where like you can't change your mind, for example, whereas like Bitcoin could potentially have like reorgs. And also I'm thinking primarily asynchronous Byzantine Agreement. So you assume there's no distinction between, you can't tell the difference between a slow and a bad node. Okay, so Byzantine Agreement protocols, they all depend on this notion of a quorum. And the idea is you pick, you have n nodes in your system traditionally, and you pick some number t, and you say, okay, any t nodes are going to constitute a quorum, and the nodes are going to vote for various statements that are part of your protocol, and if a quorum votes for a statement, it cannot change its mind. And so that means if you're kind of voting among values, for example, and a quorum votes for a value, then you know, if your quorum is big enough, that should be that'll be the only value that could ever receive a unanimous quorum. Okay, and so if you want to have safety, if you want to make sure that you know people can't vote for contradictory values, then you see that the maximum number of failures that you can survive, which I'll call f sub s, is going to be 2t minus n minus 1. Why? Because you know if your quorums are size t and you have n nodes, then the minimum overlap that you can have between two quorums is 2t minus n. So if fewer than that nodes have failed, then there'll always be at least one non-faulty node in common with any two quorums. So if two quorums all unanimously vote for a value, whichever node, honest node was in that intersection had to vote for one value, and that'll be the value that all quorums vote for. And for liveness, well, of course, you need a quorum. So it has to be the case that you can survive up to FL, which is n minus t nodes, so that you have t nodes left over, so they could actually have hope of forming a quorum. Typically, people set n to be 3f plus 1 and t to be 2f plus 1, because that's kind of the equilibrium point where fs and fl are the same. But as you'll see in a little bit, for the purposes of this talk, it's pretty important that we keep those distinct so that if we're trying to translate a protocol from a centralized model to the Federated Byzantine Agreement model, whenever the letter F appears, we have to ask, like, well, is that FL or is that FS? Okay. Now, so voting itself on like kind of what to put in like a blockchain ledger, you wouldn't want to vote directly on that question, right? And the reason is that a vote can get stuck, right? So in this case, let's say that you have T nodes, so you have a quorum that all voted for some statement A, and then maybe there's some other nodes that voted like for the contradictory, what I say A bar will be like the opposite of A or something. Because T nodes have voted for A, you know that not A or A bar is never going to get a quorum, right? Assuming you don't have too many failures. So in that case, that we'll say that the system is avalent, right? And it's great if the system is avalent, but the problem is that what if a node fails after it votes? It could have failed before everybody learned about its votes. It could have failed even before anybody learned about its votes, but before anybody learned about its votes, but after it had externalized the value A somehow. And so this is a problem. This means that the system will never realize that A had received a quorum. And what's worse is, well, here we were lucky and everybody voted for A, but imagine like all the nodes vote for like different values, right? Then of course you'll also never get a quorum because you're not allowed to change your vote. So this kind of voting mechanism has the following possible outputs, right? You start in this case that I'll call bivalent, where anything's possible. If you're lucky, you'll get a quorum that will all vote for A or all vote for not A, and then the system will be avalent or not avalent. But what we really want to do is have the whole system agree on A, and kind of, so that means like everybody, all the non-faulty nodes in the system have to kind of realize that the system is avalent, and you know, realize that everybody will realize that it's avalent, and so on, in order to have agreed on something. Otherwise, nodes may get stuck if you assume that everybody thinks A is the only possible value, but some nodes won't be able to figure that out. Yeah, so put another way, you know, how do you know you've gotten to this agreed upon stage? Well, as we said a couple of slides ago, if you have fs plus 1 nodes, fs being your safety fault tolerance, all malicious, the system's kind of lost safety, right? This intersection of these two quorums can all lie to you, so you're in trouble. So now suppose you have fs plus 1 nodes that all say to you, hey, we actually know that a quorum voted for A, like we saw this. Well, there's one of two things is possible, right? It's possible that they're all lying to you, in which case you kind of have no guarantee of safety anyway. Or it's possible that at least one of them is telling the truth, and a quorum did vote for A. So kind of either way, you can assume that a quorum voted for A without losing any safety, right? This is kind of like backwards reasoning. It's kind of like, well, I'm either screwed anyway, or like, you know, I might as well trust you, right? And so now let's say that we kind of extend this and we have FL plus FS plus 1 nodes that all make this same assertion, right? So it's possible that up to FL of these might fail, right? And if that so if more than FL of these fail, then we don't have liveness, right? So we're stuck anyway. But if only up to FL of them fail, then that means that there are going to be FS plus 1 nodes that like stick around and keep being willing to like reiterate the fact that they saw a quorum vote for A. And so that's enough to convince any stragglers in the system that in fact the system reached the avalent state, right? So what that means is that when you CFS plus FL plus 1 nodes all say that the value A reached got a quorum, then that means that kind of like you can assume that everyone will learn that basically by eventually, right? Even if they're slow, once they get back on the network. Okay, so what's different when we introduce these quorum slices? And instead of T, we talk about this weirder notion of quorum that arises from like these individual decisions about quorum slices. So at a high level, it looks the same, right? You can have split votes, you can have nodes that die after vote. Once you see a quorum, you know the system is avalent. And so the temptation is, well, can we like apply the same reasoning as we had before? Like you see the intersection of two quorums, say like, hey, we voted for A, or we saw a quorum vote for A, and so you say, well, you know, either I'm screwed or I might as well, or this is true. So unfortunately not. This is where things change, right? So before, you had this premise that the whole system couldn't fail, right? Whereas now in the federated case, failure is kind of in the in the eye of the beholder, right? In the sense that, like back in this example, right? We had V7 and V8 like didn't believe this, but V5 and V6 would have believed it, right? Because they had different quorum slices, and so V7 and V8 have to say, you know what? The fact that V5 and V6 may be getting screwed over by these big banks, like we don't care. Like that doesn't mean we should assume what the big banks are saying is true, right? So. So basically, this is where things get a little bit more complicated in the FBA model, right? What this means, basically, in the FBA model, there's no equivalent of FS plus 1. There's no such thing as saying, well, this set is the entire intersection of two quorums, therefore, like one of them has to be honest. So when you're translating your algorithm over, any place FS appears, or you say wait for FS plus 1 nodes or something, like you can't do that. What this means is that the only way to know that the system is avalent is to be kind of part of a first-hand quorum that you belong to that all votes for A. And so that's particularly problematic because once you've voted for something else like not A, you can't change your mind and vote for A. So you no longer have this ability to recover after having voted wrong by like observing some other quorum that you're not a member of that voted a different way. Okay, so we'll look at how to actually solve this. But first I want to give kind of one more piece of background, which is, I think, a helpful way to look at all Byzantine Agreement algorithms, because there's basically 5 tricks in Byzantine Agreement algorithms, and the same 4 of them, or various subsets of the same 4 of them kind of appear in all these algorithms, and so it's useful to kind of map everything down to these 5 tricks, right? And the tricks basically fall into 2 categories. There's tricks that make all nodes likely, or at least eventually, all kind of vote for the same value, because you don't get stuck if everybody votes the same way. And then the second set of tricks is that, well, since votes can't get stuck, you need a way of, instead of voting on what you actually care about, you need to vote on something slightly different that will help you determine what you care about, but where if that vote gets stuck, you can kind of recover from it. So the three techniques that help you do the first one, namely kind of ensure that eventually people are likely all to vote for the same thing, one that's used a lot is to assume some kind of partial synchrony, right? So you have basically a synchronous consensus protocol that is completely unsafe. It fails if like your network communication is too slow, but if network communication is fast, then it works. And so you kind of hope network communication is fast, and you use this to kind of get something you can plug into an asynchronous consensus protocol, right? So an example of this would be leader election, right? Where you pick a leader and then the leader tells you something, and if everybody votes what the leader said, and if the leader was honest, and if it all happened fast enough, then everybody will vote the same way. But if the leader was malicious, or if the network was slow enough that some people thought the leader had failed or something, then it won't work. But that's okay, because we're gonna plug it into an asynchronous protocol that will be safe even if people vote different ways. The second technique, and this is the one that's not used that much in practice, is just kind of have everybody flip a coin when they decide how to vote. And that's like super cool in that it works and it terminates with probability 1, because eventually everybody's going to flip the same coin, but it tends to take like exponential expected time, and so it's not that useful in practice. But there's kind of a twist on this that was an idea proposed by Rabin, which is to do a common coin. And this actually works pretty well. So the idea is, instead of flipping a coin, a truly random coin, everybody's going to flip the same coin, but they're going to flip it in such a way that the attacker or a malicious network doesn't know what the value of the coin is before deciding whose message is to delay. So you basically do this with you could do this with like a threshold RSA signature, right? Where you sign the round number, and then that signature, you'll be able to sign it as long as just like a threshold of nodes is up, but then obviously, like the attacker can't forge an RSA signature. So, okay. So more kind of the subtler part of most of these protocols is, how do you survive stuck votes? And here there are basically two approaches. The first is what I'll call the view-based approach, because it was introduced by view-stamped replication. And the idea is that you're going to vote on what goes into various kind of slots of a log. And then you're going to vote on like which log entries actually matter. So that if the first one gets stuck, it sort of doesn't matter. So imagine that you have, a view here. You're kind of creating this log. There's operation 1, operation 2, operation 3. Operation 4, we're not sure. Like some nodes voted for operation 4, others didn't, or like didn't hear about it in time and thought, you know what, the leader who is proposing 4 must have failed or something. So like, let's initiate some kind of recovery and just start again and start a new log that starts after operation 3 here. And so now you vote to start a new log after operation 3. If that succeeds, great. It doesn't matter that we don't know what went in this box, that we never agreed on that, because that's not part of the state that we're going to apply. Those transactions don't get applied to our blockchain, basically. However, it could be that enough people voted for op4 that they say, you know what, I'm not comfortable voting for this view that starts after op3, because for all I know, op4 did commit. And so that's okay, because the vote to kind of create this log here can fail, and that's no problem. You just vote to create another log, right? And so this here would say log2 or view 2 in the view stamp replication terminology failed, and so we start a new view after operation 4 here. So that's one approach. The second approach is that basically before you even vote for a particular value, you first have to kind of vote that value is safe based on like anything that had happened previously. So the idea is you're going to go through kind of rounds of your protocol, and let's say that in round 2 something weird happened where like everybody agreed that the value f was safe, but we don't know if the vote on F actually succeeded. So that one maybe kind of got stuck. So then when you get to round 3, you say, okay, look, we know that we didn't vote for any of these other values like A, B, C, D, E, G, or H in the previous round. Therefore, it's safe to vote for F regardless of what happened in the previous round. And so then you can vote for F and decide to choose F. So the protocol that I'm going to tell you about takes 2 of these tricks. It takes the partial synchrony via a synchronous consensus protocol, and then it uses this like vote for values that are safe kind of trick. Okay, so the main idea, okay, so Stellar, it has some conditions under which it guarantees safety, and namely that nodes are intertwined. That basically means that after you delete all the malicious nodes, that you have any two intertwined nodes, means any two quorums that include those will also include a non-faulty node. And it won't get stuck if you have an intact quorum, which means that there's a quorum such that even if you delete all the nodes that are not in that quorum, you still have quorum intersection. The core idea in the protocol is that you send out these vote messages that are digitally signed, but the vote messages also include your quorum slice. So this lets you kind of dynamically learn about quorums by hearing about nodes' quorum slices. Okay, so of course, a key ingredient in this protocol is this notion of seeing a quorum that all voted for some statement A. And so when that happens, when you're part of a quorum that all voted for some statement A, I'll say that the quorum ratified A, or any node in that quorum ratified A. And it's relatively easy to show that if you have nodes that are intertwined, that any two quorums that ratify a value will have to ratify the same value. You can't ratify contradictory values because, again, because of that quorum intersection, whoever's in the intersection would have had to vote one way or the other, right? The problem is, as we kind of talked about before, even if you're in a well-behaved quorum, you might have voted the wrong way. And of course, you may also have, or nodes have failed. And this is particularly problematic for the federated model because you have to be part of a quorum. You can't observe some other quorum that you're not a part of. So, so here's kind of the second idea, which is, let's say that your node V1 here, you voted for not A, and your quorum slices are kind of any three out of these four nodes. And you notice that two of these nodes say, well, actually, the system is avalent. Like, we saw a quorum vote for this. So if that's the case, they could be lying. And if they're lying, you've lost liveness, right? Because every single one of your quorum slices contains a bad node. So you'll never have a quorum that doesn't contain a bad node. So that you have no hope of guaranteeing liveness. Otherwise, this is actually true, right? So this leads to this notion of accepting a statement that's a little bit weaker than ratifying. We say that if there's if you're in a quorum and every node in that quorum voted for A or accepted A, then you accept A as well. So that's kind of the first-hand ratifying A. Or there's a second criterion. You accept a statement if every single one of your quorum slices contains a node that has accepted that statement. Right? And so that second one provides us a way of accepting a statement after you've voted against it. But we're not done yet because now you can have intertwined nodes that actually accept contradictory statements because we've kind of like weakened. It's easier to accept something than to ratify it. And also there's still no guarantee that like all the intact nodes will actually be able to accept the statement. And so the intuition for what's going on here is that what we really wanted to do was say like wait for a set that's of size fs plus 1, and then like we know we can believe what they say without a loss of safety. And we don't have any equivalent of fs. So instead we waited for a set of size fl plus 1, and now we basically said, well, either this is true or I've lost liveness, but like so I'm less sure of it than I would be in a centralized algorithm where I could wait for fs plus 1. So the solution, just have one more vote, right? So you have a second vote on the fact that the first vote succeeded, right? And so we'll say that a quorum confirms a statement A. When they ratify the statement, we all accepted A, right? And so this solves both problems we had in the previous slide. It solves the second problem, the suboptimal safety, by the fact that now we have straight up ratification. There's nothing about every one of your quorum slices or whatever. You have to be in a quorum that confirms something. But it also solves this the first problem we saw, which is of live nodes being unable to accept, right? Because you're not going to get a split vote the second time around. If you're an honest node, you might vote against A, but you won't vote against the fact that A was accepted, right? Unless, of course, you have enough failures in all your quorum slices that you're not guaranteed liveness in the first place. And so basically what the key theorem that I show in SCP is if you have a single node in an intact quorum that confirms a statement A, eventually all the nodes are guaranteed to confirm that statement. Okay, so there's a lot of mechanisms here, so let me kind of summarize it with a picture. And does the fact that the clock disappeared mean I'm out of time? Or,
no, keep going.
Okay. Oh, now it's no CP, DHCP. DHCP, oh, great. The clock pieces. Okay, so here's kind of a summary. You start in this kind of uncommitted state. You might vote for some statement A. You might vote against the statement A. Then, if a node in every one of your quorum slices accepts A, you accept A. But also, if you're part of a quorum that votes for or accepts A, you accept A. And then you have the second kind of confirmation vote. And if you're in a quorum that accepts A, then you've confirmed A. And when you've confirmed A, you're sort of guaranteed both the kind of the safety property that you want, that if you're intertwined, you won't confirm contradictory statements, and this property that's useful for liveness, namely that if you're in an intact quorum, all the nodes will eventually confirm A. So we turn this into a consensus protocol using the kind of two-phase trick that a lot of systems use, where first we're going to have a synchronous agreement protocol, and then an asynchronous one. So the synchronous agreement protocol just has nodes call out votes to nominate values. And you're not allowed to vote against nominating a value. You can vote to nominate a value, or you can not have expressed an opinion on that value yet, but you can't vote against it. And so this means a vote to nominate can never get stuck. So what you do is you have people vote for values, and then when they see nominations, they kind of echo those votes and also vote to nominate those values. Until such point as there's a single value, you have confirmed nominated at least one value. And then you still accept nominated values, but you don't vote to nominate any more values. And so what this means is eventually all the nodes are going to converge on the exact same set of nominated values, right? Because eventually some value is going to get nominated, and then once it does, confirmed nominated, once it does, everybody in the whole, all the intact nodes will agree that that was nominated. Then they'll stop voting for new things. So then there's only so many votes kind of trickling around in the background before everybody agrees on the exact set of nominated values. And once you have that set, you can kind of combine it in a deterministic way, like take the union of all transactions and transaction sets, for example, or the one with the highest hash, or whatever you want, right? So this is great. It almost looks like we've solved the problem, right? So just run nomination. If you wait long enough, everybody will have the same value. The problem is you don't know when you've waited long enough, right? And if you did, you would be violating this FLP impossibility result. So like this can't possibly work. So what you do is you kind of assume that you're done, but you don't, but you're not, or you don't assume, but you kind of take it as a working assumption. And you run it into this second round of the protocol, which is this balloting protocol, which uses the other trick of only voting for safe values that I told you before. So here you're basically going to assign counters to these rounds, and you're going to basically vote to prepare a value, which essentially says that that value X here is safe in round one. And then if it is safe, then you can vote to commit 1, X, and once it's committed, then you output the value X. So here's kind of the balloting, like in a more detailed example. Suppose for simplicity, we're deciding between 8 different values, A through H, initially. And what you're really going to do is kind of the assembly language of these prepare and commit messages is that you're voting to commit and abort these individual ballots that consist of a counter that's like your round number and then a candidate value. So the first thing you do is you prepare the value 1, G by basically voting to abort everything less than 1, G that also has a value other than G. And then you vote to commit 1, G, but you might lose that vote, right? And so if you lose that vote, no problem. You try again in round 2. Maybe in round 2, we decide that 2, F is safe. And so then you vote to commit 2, F. That vote could get stuck. Right, so suppose that vote gets stuck. We don't know it's stuck. We just kind of suspect it's stuck because you'll never know for sure that it's stuck. But it doesn't seem to be willing to finish. So you go on to round 3, and in round 3 you say, okay, look, what we do know is that for everything less than 3 comma f, there's no possibility that any of these other values made it in a previous round, right? All these x's are here. We just don't know what's in the prohibited sign here. So that means that value f here is safe in round 3. So let's vote to, now that we've agreed that that's safe, we can vote to commit 3 comma f. And then once that commits, then you know that the output value is f. So the key invariant here is that all the committed and all the stuck ballots actually have the same value. Okay, so SCP is used in the real world by Stellar, which is, like a top 10 blockchain with a built-in DEX, and is really optimized for people who want to issue tokens for everything from like carbon credits to real estate shares to car repossession tokens, whatever those are, but like that's a big one, to in-app currency, whatever. Blockchain people come up with crazy ideas on blockchains. And kind of, we think that this is much better than mining for kind of real-world assets, because real-world assets tend to be backed by a counterparty, and so that counterparty, if you're Citibank, you're issuing a bunch of digital dollars, you can't afford to have like Bitcoin Cash, ABC, and SV, like those can split off, and that's fine because like you're duplicating the digital coins in each branch of the fork. But you can't duplicate dollars that actually have to be backed by bills that are sitting in a vault somewhere. So it's much better if you're issuing assets to say, okay, my assets will be redeemed by a machine that like believes in this quorum slice or like this particular validator that I run myself. And so like just if you care about my assets, make sure you're in sync with me. Other blockchains are now adopting this. MobileCoin and Cent are two kind of big ones. And I think ultimately there are a lot of applications beyond blockchain. So we could imagine like a better version of certificate transparency, or maybe like firmware transparency. Before Apple can upgrade the bootloader on your iPhone, maybe they should need to like publish that in like this like public transparency log, and the EFF should be able to be in your quorum slice, for example. Also, there's examples of like delegated namespaces where Stanford should be able to give me a certificate for my email address, but then they shouldn't be able to be coerced into overriding that certificate. So for like 1 year or something, they should be able to like delegate that certificate to me. And again, if the whole world is keeping everybody honest by putting all these certificates or putting all the revocations into a log with this kind of protocol, this model would be possible. And again, you don't want to do it with mining because you don't want to put a price on like how much does it cost to like undermine my certificate, right? I want to say like, okay, I just trust the EFF, and like they're going to scream bloody murder if someone like tries to steal my email, and I don't care how many machines they have or how big a mining rig or whatever. Okay, questions? Yeah.
How does how does communication complexity scale in the number of candidate values?
Oh, in the number of candidate values, it doesn't. It's constant because even though conceptually you are like voting for like an exponential number of aborts, those are like just encoded with a with like a prepare and commit statement. So the individual votes on ballots are like conceptual for like proving the safety of the protocol, but like you don't actually need to do that. Yeah. Other question.
Yeah, my question was I think similar. So very nice protocol. I like it.
Thanks.
Could we? So the question is around scalability. Could we actually ever see it on 1 million nodes, or what is the limit here?
Right. So
There would be a lot of communication.
you could do 1 million nodes, but you couldn't do 1 million nodes where like everybody had 1 million nodes in their quorum slices, right? So the hypothesis here is like, could BGP scale to like 1 million like tier 1 ISPs or something? Like, probably not. I don't know. But the idea is that like we want market forces to kind of create a hierarchy. And so like most people, we think that like, you don't have to exactly believe in the hierarchy, but like for the most part, there'll probably be some core of like, a dozen to like maybe a few hundred nodes that are the ones that like are actually really important. But we don't have to like decide, the market can decide what's important and you don't have to agree, right? Those are like the two important properties.
And MobileCoin is running it on mobile phones?
No, they're running it on the server-side infrastructure, I think.
So it's all centralized, then it's not a decentralized system.
It's just like running a bunch of servers somewhere.
Yeah, I mean, I think in the long run, I believe I can't really speak for MobileCoin, but I believe the vision is that they have this two-tiered thing where they're actually using Intel SGX, but they're only using SGX for privacy. They don't want you to be able to steal money. So the SCP is basically a way to, so like you can be running this, and then even if SGX is broken and someone like figures out who owns how many coins and whatever, as long as like the people running the machine are honest and the part like running outside of SGX is honest, like SCP will make sure that that works out. Yeah.
Can you talk about implementations? Like what? So clearly you have one implementation in Stellar. Is that something? How easy is it to use SCP to run other consensus for like a game, for example, or something else?
Yeah, so I would like there to be, so there are multiple implementations. There's not like a really good one that's easy to plug into your own application. And I'm working on standardizing, on getting an RFC through the IRTF. But none of the implementations interoperate, and there's actually a reason for this, which is that this needs to run on top of some kind of multicast protocol. And there's the huge, like the dirty secret of all this blockchain stuff is like, we talk about all this consensus stuff, but they're all vulnerable to Eclipse attacks because the overlay networks completely suck, right? And so like so I'm specifying the protocol in such a way that it's orthogonal to the overlay network because like that's an open problem. Now, my hope someday, or my idea is that like maybe quorum slices could actually provide a solution to the overlay problem as well, in the sense that you could create an overlay network that's like it's not optimally efficient, but it's like reasonably efficient, but also it's not vulnerable to like Sybil attacks and Byzantine actors, assuming that like, you know, some whatever properties of your quorum slices that you're already assuming for consensus are true. So that would be like a super cool result. Anyone wants to like work on that, you know.
Yeah, that would sort of be like a reliable broadcast type.
Well, it would be like, you know, like split stream or whatever, like any of the, you know, I mean, right now, I think a lot of blockchains do kind of the moral equivalent of Gnutella or whatever, you know, they're like basically like flooding messages. And so that's going to be a bottleneck, right? I think like long before consensus is a bottleneck, because you can amortize consensus over arbitrarily many transactions, but you can't broadcast arbitrarily many transactions over a super crappy and wasteful overlay network. So then there's all the DHT-based solutions that are better, but those are vulnerable to Sybil attacks. And so the question is, can you, and actually, we're actually in the worst of both worlds. We're doing like Gnutella, but Gnutella plus Eclipse attacks, right? So it's really bad, like what's happening with the multicast. And so like, I don't know what the solution is, but like quorum slices might help. Like that's just a complete like conjecture, but with no idea of how to actually solve it. Yeah?
If your quorum slice gets into, is there any chance of loops happening there that cause
You want loops. You want loops. It's good. So I don't have the support slide, but that's, it's good.
One-step loops of banks.
Yeah. But you could have like crazy loops that you would never want to engineer in, but like could happen by accident. And it's fine because all you're doing is you're just broadcasting. I'm not waiting for you. I'm just saying like, I believe this if you believe it, right? And you say like, well, like you believe it if I believe it, right? And so now we assemble both these messages and we say, oh good, like everybody's satisfied, right? So it's cool. And then it actually handles the loops, and you actually want that because it's healthy to have lots of like mutual dependence, right? It means that like the same parties think each other are important, and you don't want to enforce that it has to be completely symmetric and that everybody agrees who's important, but you want to leverage that when it's there. Yeah.
Does quorum composition need to be public in order to?
Yes.
How is that information disseminated?
It's literally in the vote messages you can. Well, actually, what's in the vote messages is like the SHA-256 hash of it, and then you just, if you don't have the preimage, you query it because it's like it doesn't change that often, so you might as well cache it and not use up a lot of space in the messages.
And in the case of like pretty wide-ranging loops where state is growing and in reconciling all of those becomes complicated. Is there any work happening to sort of like distribute that computation? Like, could it get into a place in which the network is such that whatever computation I have isn't actually
sufficient?
I mean, the quorum stuff is like so in the noise. I mean, at least for Stellar, like all our optimization is on like the transaction processing, right? Because the thing is like, we're doing it like every 5 seconds, right? Like 5 seconds is like an eternity for like computing a few hashes and like checking, set membership of like 100 nodes. And so what's the bottleneck is like how many transactions can you actually process in those 5 or those whatever, the 4 seconds between when you're busy like worrying about the consensus.
This is leverage protocol of like
Oh, well, so Ripple's protocol isn't safe, so there was a bug in it. They came out and said, okay, it doesn't work. Like, basically, Ripple is basically like a crappy version of a centralized thing. Like, everybody has to have the exact same, what they call a UNL, but it's you can kind of think of as quorum slices or whatever, but it's not transitive. And if you don't have at least 90% overlap, it's very bad. And so then they said, okay, to fix this, we're going to propose this protocol called Cobalt. And Cobalt is a lot more complicated than SCP. Like I don't understand like exactly what they're trying to go for, because SCP has like certain like it's like optimally safe. For example, like Cobalt's not going to do any better than that. Maybe it's as good, but it's not. But anyway, they haven't implemented it yet, so it's still like theoretical. I don't know if they are going to implement it. So what they should do is they should use SCP, but maybe like they don't like the word stellar in their consensus protocol or something. I don't know why they don't want to do that. Well, it's just hard to change your consensus protocol. Like maybe they're just never going to change it because they aren't trying to be as decentralized as we are.
So you were trying out the implementations, and then you mentioned there's one polygon and so on. Like, what would you point people to? Like, if somebody wanted to implement Stellar, would you point them to like reference implementation, or would you have a way of looking?
I know I would have them I would do to the internet draft, and a lot of people work from the internet draft, and then like when there's stuff that's unclear, you send me email and like I fix it, right? Because like it would be super helpful to have more implementations. So if you're at all interested, please do look at the internet draft, and please send me questions if things are not clear in there. I'd love to have contributions on that. Yeah.
You didn't, I think, talk about staking and finality and those sorts of things.
It's not. There's no mining. This is a Byzantine Agreement protocol. So, it has staking and finality are exactly the same as like in PBFT. Namely, like once you output a value, it's finalized, and there's no staking.
So, could one of the participants say, basically generate messages that on both sides, equivocate?
Yeah, that's a Byzantine failure. We modeled that as a Byzantine failure. And so as long as nodes are intertwined, meaning you delete all the Byzantine faulty nodes and you still have quorum intersection, then it will be safe. And as long as there's an intact quorum, then it will be live, or at least live to the extent FLP lets it won't get stuck. There'll always be hope for termination.
How is that failure actually handled in the code? Meaning, if you do enter a Byzantine setting and you end up with a bad quorum, does that kind of like halt or terminate in some way?
What do you mean a bad quorum?
Or
so let's say you don't have a quorum, right? So you have you mean you're safe but you're not live.
Maybe my quorum slice is all malicious and lies to me, but they say something else to the rest of the world.
Right. Well, yeah. Then you're host. You should throw out your.
But how do I detect that? I guess the point is, how do I detect that?
I mean, it's subjective, right? It could be that, like, maybe what actually happens is I don't know, like all the Russian nodes think one thing and all the American nodes have another, and you really do have a fork, right? And so what you have to ask yourself is like, okay, there's a bunch of tokens I care about. Where are their validators? Like, which side am I going to be able to redeem my tokens on? And then based on that, you'll decide if you have a problem or not.
Yeah, exactly. I mean, like, you could be detecting that after some period of time, votes from certain parties that you care about are not appearing, and then therefore detect that you're a host in this fork, and then use that to recover. Either like. I
mean, the recovery is like fairly heavyweight. I mean, you can just model recovery as like throw away your node and just like bring up a new node with like a new public key or something, right? So there's not like a kind of like an in protocol automatic recovery, because we're like trying to avoid the failure in the first place. Also, if this does happen, it would be like it's like how they. I mean, again, I think about this a lot in terms of like internet peering, right? And so like there's this thing that happens in internet peering is that you do have this like brinksmanship that happens, right? So like, you know, at one point there's this famous story where like level 3 went up to Cogent and was like, so we're peering Cogent, but like you're not really a tier 1 ISP. How about you buy transit from us or we de-peer you? And Cogent said, I dare you. Right, and so level 3 de-peered Cogent. Both of their customers screamed bloody murder, but Cogent was like way less expensive than level 3. So like Cogent's customers were kind of used to like using Cogent where it worked because it was cheaper, and then using something else. And so ultimately, probably level 3 caved, but there was some like secret settlement, and then they kind of like you know, re-peered, right? And so like I can see like exactly the same thing happening in like this consensus world. Like imagine that you're in a situation where the US comes and goes to like, or the government comes to all the banks and says, you cannot approve any block that includes transactions. You cannot vote for any block that includes transactions from these people in Cuba, right? And so the US says, okay, like I guess we can't vote for those. But then like nodes in Europe do vote for them, right? And then, oh my God, the network grinds to a halt. So the Europeans are like, hey, we're just gonna like de-peer you. We're gonna remove you from our quorum slices if you don't start participating, obeying the protocol, and actually voting for these blocks where we need your votes to proceed. And so then the US again has a choice. If the US doesn't do it, well then Europe will remove them from their quorum slices and start accepting these blocks and moving on. So then the US, according to the protocol, will say, well, I didn't vote for it, but I'm going to accept it because like a blocking group has done that. And so then the regulators could come back and be like, no, you have to do something even more extreme. So then they can say, well, I guess we could, you know, fork ourselves from like the world's banking system, right? And maybe the US is big enough that like we could actually afford to do that, and other people would have to play ball. But it's totally this like brinksmanship thing, and that's ultimately what you want, right? It's like how important someone is should like determine what, you know, what role they play. And the conjecture is that the pain of having like these totally disjoint banking systems where you can't do transactions across Europe and the US is so high that the regulators wouldn't like force the US to like de-peer Europe and like fork the network. But, you know, you don't know, right? Like that's
Would you see that
that's the hypothesis.
And that tussling and so on be reflected in layers and layers of client software, meaning if that happens and there's some kind of reversions and so on, you still need applications to be able to deal with that without like dumping all their state and like starting from scratch.
Maybe, but like I mean, the hope is that it doesn't happen. In the same way, like yes, people like clients have multiple internet service providers, but for the most part, like if you don't have the connectivity, it's like bad things happen, right? So, I mean, I think it'll be like a similar thing. Like yes, big banks will always have multiple payment rails, and even if like blockchain becomes like the cheapest one, like I'm sure Swift will still exist in like 30 years, and there will still be, you know, some amount of like old school reconciliation on Excel spreadsheets or whatever. But the hope is that like this stuff becomes cheaper and like easier, and it works really well, and that like people don't want to break it. Yeah.
I think I may be getting to the same point, but in cases where like separate networks merge, how would you deal with past transactions?
I mean, you can't. There's only one winner, right? So this is where maybe the internet analogy breaks down, in that you know, Cogent and level 3 can re-peer and claim everybody comes out a winner, whereas like here there's only one winner, right? Or I guess you could say like, great, let's have some compromised state where we don't import anybody's history and we just start over again fresh.
Yeah,
but
I think what we're getting at is you could model those failures and that recovery, and then have it as part of the protocol that this might happen at some point, and you understand how to hook into it.
Maybe. I mean, I just think it's like so subjective what happens. This really comes down to like human level negotiations, I think. Like you want to avoid this at all costs, and so you want to make it, you know, very expensive for this ever to happen, because you want to incentivize everybody to be part of the same network. But then, and that will actually reduce the chances of it actually happening. But then if it does happen, you know, it is going to have to be this painful thing, because otherwise people would just make it happen if it weren't painful enough, right? Other questions?
Be a very silly question, just for context. So all the nodes of the protocol, are they known in advance, or how does a new node join if they want to join?
You just join. So you pick some quorum slices, probably based on the validators that of the assets that you care about, and then you join. Now, you need a quorum slice. That doesn't mean you're going to be in other people's quorum slices, but it's the same way. It's like, can you plug your webcam into the internet? Yes. And nobody cares if it's plugged in or not, but you might care that it can like reach Nest or, you know, like other places. But then if you become important, people will say, oh, I want to stay in sync with you, so I'm going to add you to my quorum slices.
Oh, got it. So the main Sybil attack protection here is that if you create a million nodes that nobody
Yeah, nobody cares, exactly.
They never care, or they care themselves. They
Yeah.
only link amongst
Yeah.
themselves, but okay, got it.
Yeah.
And that's kind of manually set up. Like you manually get construct your quorum slice and you point to who you connect to and so on.
That's right. There's like in your like stellar
Okay.
conf file, you say like what your quorum slices are. Exactly. The way we specify it. In the talk, of course, the protocol works in some abstract specification, but like you want to specify it fairly compactly. So we just have this like hierarchical thing where it's like at the top it's like a K of n, and each of those K can either be like directly the public key of a node or like recursively another K of n thing, and it can go like 2 levels deep. So we think that that's good enough, and it kind of reflects the fact that, you know, there's these organizations, and for each organization you don't want them all to be up, but you might want like K of n organizations or even n of n organizations where each is like K of n nodes. Oh, another question.
In practice, do you have enough scale yet to tell how much inertia people have around adding other folks into their quorum slices? Because if it's say, I've got to go in and do a manual thing to add you, next week.
Yeah, I mean that's fine. Like we don't necessarily want you to add lots of people. I mean, what we basically want to do is, look, right now everybody depends on like the Stellar Development Foundation, right? And like, you know, that's okay. That's not where we want to be in like, you know, like 5 years or whatever. But the important thing is that if we were to say like, you know, screw you guys, we're shutting all our nodes down, like the network would hang, but people would recover. They would say like, oh crap, now we actually have to think about this. And so there would probably be like maybe a few hours of downtime, but the system would go on, right? Like, and so it's very important that SDF not be like central to the functioning of the system, which by the way, is, so that's like another example where like Ripple would not have that property, for example. Like the network would probably not survive if Ripple went away because they need that UNL. Another question.
Yeah, thinking about this in the context of like package management,
Mm-hmm.
have you given thought to sort of negative trust?
Yeah, so this is not my idea. This is Dan Stefan at UCSD, his idea, but this is something that I think would be really cool to have on this. So one of the places where these consensus protocols are really good for is sort of freshness, right? Like knowing that you have the latest version of something. And so what we would like to do is have a way, if you're a package author and you discover a vulnerability in your package, a way for you to basically like revoke that package and kind of force people to upgrade. And so to have this kind of log that everybody agrees on. And so whenever you're installing software, like you know that you're not getting old vulnerable packages. Like that would be super cool. Other questions?
You
Yeah.
could totally plug that into a distro and have like the certificate chain and the package manager
Yeah.
like be hooked to that.
Yeah. I mean, ideally there would be like, there would be kind of like a kind of this general like transparency consensus that would be like this internet service, and you could use it for this, you could use it for like delegating, you know, certifying people's PGP keys or whatever for their email so that you can't get coerced into issuing bogus certificates. And it would be used for like firmware transparency. I'd also like to use it, you know, I hate devices where you can't unlock the bootloader. You know, at the same time, I have to admit that, like, you know, I understand like Nest's concern that the last thing you want to do is like sell someone a camera, they Airbnb their thing, and then like for one weekend, and then a year later they realize they've been spied on for a year because somebody hacked the firmware. But you know, if you can sort of like prove that like you're willing to revoke this thing in a blockchain and then prove to your device that like you've announced to the whole world that you've unlocked the bootloader, and then in exchange for that be able to unlock your bootloader, then like the OS researchers like me can like play with all these devices, but you could also have like security people. So that'd be like another place where I would like to see something like this used. Any other questions? All right, cool. Well, thank you.